Assalamu alaikum everyone. So today we will be having lecture number 29 and we will be discussing about RAM, random access memory, right? So whenever we talk about the computer system, right, so memory is an important element or component of the computer, right? And random access memory, right, is one of the type of those memories, right? So it's actually is a collection of storage cells, right? And that those cells, they can store bits, right? One storage cell can store 1 bit, right? But to get data out of that cell, right, or to store data into that cell, you need something else, right? So there has to be some circuitry that is associated in order to perform different operations, that is read and write, right? And we can access information, right, from that random access memory, and we can write information into that random access memory, right? And we can randomly access any one of the locations, right? For example, if we have a 4-bit memory that have different locations, right? So when we want to access one of the locations, so we can do that randomly, right? So this is not an incremental access, right? As we in counters, we have seen that we start counting from 0, 0, 0, then 0, 0, 1, right? So as opposed to that, we can access any one of the location randomly, right? So that's why we have named it random access memory, right? So it's a collection of storage cells, right? And we have an external circuitry, right, that is used for the input and the output, right? And we can perform different operations. We can read information from the RAM, we can write information into those cells, right? And obviously it's a collection of cells, right? So we can have different words of different lengths, right, depending upon the size of the memory, size of the RAM, right? We can use a sequence of signals, right, in order to access the data, right? And whenever we talk about the associated circuitry, right, or that is being used in order to retrieve data from the memory or write data into the memory, right? So decoders are very, very important, right? And they select the specific location of the data or the memory, right? We have two different types of RAM. One is static RAM, right, and other is the dynamic RAM, DRAM, right? So in case of static RAM loses all its contents whenever we switch off the circuitry or computer, right? So these are the preliminaries, right, regarding the RAM. So we normally gauge the data in bytes, right? A single bit, right? As we know that a flip-flop can store a single bit, right? So whenever we join different flip-flops, and we normally call it a word, right? Or we can have more than 1 bit, right? And a collection of 8-bit constitute, right, a byte. So a collection of bytes is called a word, right? So if we have 2 bytes, right, a 16-bit word contains 2 bytes, right? So it means we have 16 bits, 8 plus 8. So we normally gauge the capacity of RAM in bytes, right? For example, and you normally come across those different words, MBs and GBs, so 16 MB means 16 megabyte, right? So we can perform different operations, right? Write operation for writing data, right, or specific word, right? Read operation, and we can read data, right, from specific location, right? So, and we have different symbolic representation. So this is the conventional symbol for the OR gate, right? And here, if I put those vertical lines, right, so I will call it an array logic symbol, right? So this is the conventional and array logic diagram, right, for OR gate. So here is the block diagram of a RAM, right? So you can see that we have different interfaces and different signals and different data inputs, right, and control signals. So here you can see that we have the data input, right, and this is the data out, and these are the addresses, right? So we will be applying address over here, right, and these are the control signals, read and write, right? So this is the size 16 into 8, right? So k address lines, right? If we have k address lines, so we can have 2 raised to power k different words, right? So an n bit per word, right? So this is the n data input lines, right, and this is read, write, and n data output lines, right? So this is the 2 raised to power k. If we have k address lines, then we can have 2 raised to power k unique words, right? K address line, select one of the words, right? So if you want to select one of the words, right, so we need to generate the address, right, by using the decoder, right? You can read and write data, right? So here these are some of the fundamentals regarding RAM, right? So here we have taken a very simple example, 8 words of 2 byte each, right? So it means each word is of length 16 bit, right? So how many address bits we need, right? Do we need? So if I talk about the decimal, right? So you can see that 0, 1, 2 up to 7. So how many bits I need in order to represent those different decimal values? So obviously 8, right? So you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, right? So these are the 8 different locations. Each location has 2 bytes or 16 bits, right? So this is a word with a length of 16 bit each, right? So in order to address all those 8 different locations, what I need 3 bits, right? So that's why I mentioned the decimal, right, and then the corresponding binary, right? So what I will be doing, right, so we will be having so I will be having 0, 0, 0, right, for this, right, for this 0, 0, 1, right, for this 0, 1, 0, right, for this location the address is 0, 1, 1, right? For this location I will be having 1, 0, 0, right? For this 1, 0, 1, 1, 1, 0, and for this I have 1, 1, 1, right? So we have 8 different locations, right? So for each bit I need a 1 binary cell, right? So how we will be evaluating the size of a RAM, right? So if we have k words, right, k different words, right, so how many bits we need? We need k address bits, right, and 2 raised to power 3 words, 3 address bits, right? So here you can see and how many locations we will be having, right? 0 to 2k 2 raised to power k minus 1, right? So memory address, right? So this is the binary and this is the decimal 0, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we have 10 bits and these bits are reserved for the size, right, for the addressing. So 2 raised to power 10, right, so it means 1024 addresses, unique addresses we can have, right. And if I have, this is the length of each word, right, 16 bits or 2 byte, right. So how I will be evaluating or calculating the size, right. So that is 2 raised to power 10 into 16, right. So that is the content, 24 into 16, right. So that is the size of the, right. So normally we use some subscripts, right. 2 raised to power 10 for kilo, 2 raised to power 20 for mega, and 2 raised to power 30 for giga, right. So we can have the, so normally nowadays we come across this very frequently, giga, because now the RAMs are in giga, right, even for personal computers or even for tablets, right. So here we have the write operation, right. So what we need to do, we need to go through those 3 steps, right. So here you can see that we have the block diagram mentioning the data input lines, these are the data output lines, right, and this is the memory unit. We have 2 raised to power k words and bits per word, right. So it means we need k address lines. This is the control signal read, this is the control signal write, right. So what we need to do, right, first we have to apply address of the word to address line, right. So we need a circuitry that can generate the address of the location where we have to perform the write operation, or so. And after the generation of the address, the second step is we have to apply the input data, right. So we will be applying the data over here in order to write that data onto that memory, right. And then after those 2 steps, the final step is we will activate the write, right. So we will perform the write operation. So here you can see that we are not using the data out lines, right. So it means the read operation should be, or the read control should be inactive, right. So here we have the read operation. After the write, we can read data that is already available or stored within the RAM, right. So what we will be doing, this is the, right, again block diagram, right, this address lines, read and write, right. So here we will be performing 2 operations, right, because here we have to make sure that the input data is available, right, but here we don't need the input data, right, we only need to take the data out, right. So what we will be doing, we will be generating the address, right, which we have to read, right. So the circuitry which is addressing those different memory locations, right, that circuitry will generate the address of the location where the word is there and we want to read that location, right. And after that, after generation of the address, we simply have to read, right. So here you can see that the input lines are not used, right, and so it means this write operation is associated with this data input lines, so that has to be inactive, right. So these are the steps we have to go through in order to perform the read operation, right. And then here we have the memory timing, right, for write operation, right. So So it's a random access memory. So one of the main point over here that memory doesn't use the clock, right? But the control signals, if I talk about the control signals, so those different read and write operations, they are clocked. They can be clocked, right? May be generated on clock edges, right? So cycle time, what cycle time is time needed to write to the memory, right? So that is the write cycle, and then we can also have the read cycle, right? So write cycle, if the cycle time is 15 nanosecond, it means 3 clock edges required, right? So here you can see that each clock cycle is of 20 nanosecond, right? So if I have this clock, right, so this is the rising edge and this is the falling edge, right? This is the rising edge. So from this to this, right? So we have 20 seconds of time, right? So 20 plus 20, 40, and I need another clock, right? I cannot have the half clock whenever I talk about the clock, so it will be 1 clock, right? So I need 3 cycles, right? Clock edge is required, right? So T1, T2 and T3, right? Because I will be talking about the edges, right? So I need this edge, and this edge, right? So this is 20 and this edge is also, right? So I need 3 edges, right, in order to accommodate a cycle time of 15 nanosecond, right? So here we have the memory address. We need to make sure that address is valid, right? After the validation of the address, right, we enable the memory, right, and then we will perform read or write, whatever is required, right? So here we have the write, and then finally we have to validate the data, right? So this is the write cycle, and here we have the read cycle or read operation, right? So how much time is required in order to access the memory location, right? So you can see that again here we need 3 T's, right? Right? So 50 nanoseconds. So you can see that for 50 nanoseconds we have again over here 3 edges, right? So we need 3 edges, right? 3 clocks. So the steps are the same. First we generate the address, right? Then we enable the memory, and then we will read the corresponding location, and output data has to be available, right? Has to be made available, right? Right. So whenever we talk about the computer system, right, so there are certain components that are very important, and one of the component is CPU, that is normally considered the brain of the computer system, right? So for memory, right, the processor generate control signals, right, address and data, right, and the values that are generated by the processor, right, they are stored, right, in the RAM, and whenever required they are read from the same RAM, right? So the timing of the overall system is very, very important, right? Because if I want to buy a computer, I will be interested to have a very good computer, right, that can work fastly, right? So that includes the timing, right? Or you can say that the processor clock speed, gigahertz or something like that, right? So in case of CPU, right, processing is a central processing unit. It provides data for the cycle time whenever we want to write, right? On the other hand, the processor has to wait for the access time for different reads, right? Read operations. Then let's talk about different types of memory, right? We have different types of memory. Static RAM, right? That is abbreviated as SDRAM, right? And then we have the DRAM, that is dynamic random access memory. So in case of static RAM, right? So we have latches, right? And once value is written, it is guaranteed to remain, right? As long as the power is applied, right? So it's expensive, right? And it has built-in processor. If we have a SRAM chip, the processor has to be built inside the chip, right? On the other hand, DRAM, right? They are simpler, right? And it needs refreshing, right? So data has to be rewritten after predefined amount of time, otherwise the data will be lost, right? And we normally use DRAM whenever we have to handle large amount of data, right? And its access time is longer than SRAM, right? And we use DRAM as the main memory within the computer system, right? So here I have shown SDRAM, right? So this is a synchronous DRAM, right? So you have seen those in your personal computers, right? And we have different modules, right? So you can see that if this is a module of 1 giga, right? So within the motherboard of a computer system, we have different slots, right? So we can plug different modules, right? So if we want to have, or we want to upgrade the RAM, right? So they are connected to the CPU via 64-bit bus, right? And we normally calculate the speed in megahertz, right? So we have different names: PC66, PC100, and PC133, right? And they can run at 66 megahertz, 100 megahertz, 133 megahertz respectively, right? So how we will be calculating the bandwidth, right? Because the amount of data that can be sent over the bus between the CPU and the memory, right? So memory bandwidth can be computed by multiplying the number of transfers per second by the size of each transfer, right? Okay, then we have another sort of memory, right? DDR-RAM, right? So that is the double data rate, or DDR-RAM, right? So those they are smaller in size, right? So this is for PC and this is for laptops, right? So it's a double data rate. So why we call it a double data rate? Because it can transfer data on the negative and the positive clock edge, right? So it can function on both positive and negative clock edges, right? Similarly, we have the same sort of speeds, 100, 133 megahertz buses, right? So another difference is that it consumes less power as compared to SDRAM, right? So SDRAM is being operated at 3.3 volt. So for this we have 2.5 volts, right? So then we have RDRAM, that is ROM bus, right? And it has a 16-bit bus only, right? But the memory runs at a faster speed and the data can be transferred on both positive and negative clock cycles, right? So this is the RDRAM, right? It's almost obsolete now, and it is difficult to find this RD. So let's talk about a single binary cell, right? So here you can see we have a single binary cell, right? And you can see that we are using some of the gates, right? And a flip-flop or latch, SR latch, right? So you can see different signals, right? This is the input, and this is the select signal, and this is the output, and this is the read and write. But this is important that we have the bar at right, because we cannot have read and write at the same time, so one has to be activated at a time, right? So select input enables the cell, right, for read and write. So first of all we have to enable, right, or this is the select, or you can say enable. Then read write input, we need to determine the mode, whatever we want to read the data from this circuitry, or we want to write data into that circuitry, right? So this is the block diagram, right? So it's same signals, but we have a block diagram as opposed to the detailed circuit over here. Input, select, output, read and write, right? So here SR latch, right? So data goes to both S and R, right? So you can see the input, right? This is the input for S, and this is the input for R, right? And then we have the select enable operation, right? Read write, and so we have to read or write, right? So this is inside story, right? So you can see we have different binary cells over here, and those binary cells, they are bundled together in order to have a word, right? So here we have a decoder, right? And that decoder is being used in order to have the addressing of those different locations, right? So this is the input data, right? So here we have the output data, and this decoder is 2x4 decoder, right? So if we have to address, right, 4 different locations, so how many right, bits I need? 0 0, right? 0 will be selected, 0 1, location 1 will be selected, 1 0, location 2 will be selected, and 1 1, location 3 will be selected, right? So we have 4 words, and these words are numbered with 0 1 2 3, and each binary cell, right, we have seen the design of binary cell or inside of binary cell, right? So each word is of length 4 bit, because each binary cell can store 1 bit each, right? And we have 4 different unique locations, right? So we need a 2x4 decoder, right? And this is the control signal, right? And here we will be applying address input whenever we want to have word 0 selected, so we will be applying 0 0 over here. When we wish to select word 1, so we will be applying 0 1 for 2, 1 0 for 3, 1 1, right? And this is the enable, and this is the read and write, right? We have to activate one operation at a time, right? Because we cannot read and write at the same time. And these are the output, right? So data will be gathered here, right? So address inputs, they go into the decoder, right? So word line selects a row of bits, right? So you can see we have rows and columns, right? So this is this row representing a unique word, right, and this column represent the output bits, right. So we will be having those columns, and right, and the output data is received after passing through the OR gate, right. So this is the 1 bit, right, so that's the same, right. So we can select one word at a time, right. So here we have another configuration, right. So what is different, right, so rather having, so you can see that each, now we have binary cells that are being attached to those OR gates, right. So we have 3-bit, right, word, right, and we have 4 words, 0, 1, 2, 3. So again we need 2 bits in order to address those different locations, right. So each binary cell can store 1 bit. So 4 words of 3-bit each, right. So has a total of 12 binary cells if I count. So those are the 12 binary cells, right. So memory enable is 0, right. All the output of the decoders are 0 and none of the memory word are selected, right. So whenever we have enable 0, right, right, so this is 0, right, so it means the decoder output are zeros and none of the memory words are selected, right. So now we have, if we want to have arrays of RAM chips, right. So whenever we talk about the array of RAM chips, right, so for example we have an application, right, so that application, it requires larger capacity, right, and single chip cannot accommodate that application, right. So in order to accommodate that application, what we need an array of RAM chips, right. So how we will be calculating the capacity of the memory, right. So normally we know the RAM size depends on 2 parameters, the number of words, right. For example, if I go back, right, so number of words, here we have 4 words, right, and the number of bits per word, right. Again, how many bits we have in this word? 3 bits, right. If I go here, for here we have 4 bits for one word, here we have 3 bits for one word, right. So these are the 2 important parameters whenever we talk about the capacity of memory, right. So if we want to increase in the number of words, right, so what we need to have more address bits, right. So if I want to increase one word, right, so what I need to address, so I need one more extra bit for address, right. So if I want to add an extra bit over here, right, so it means I want to add, or I want to increase the length of the word, right. So I can do that, right, but for that what I need to have more number of input lines, right. So these are the input lines and these are the output lines, right. So I need to have, if I want to have an extra bit over here, so I need a line over here, right, and I need a line over here, right. But I can have the same address bits, right. But on the other hand, if I want to have an extra word over here, I need an extra address line over here. So that's what has been, every bit added to the length of the address doubles the number of words, right? So if I can add one address line, so I can have how many? So 2 raised to power 3, 8, right? So it will double, right? So if I have one more 4, 2 raised to power 4, 18, 16, right? So we can have, so here is an example of array of RAM chips, right? So you can see that we have a RAM 1K into 8, right? So it can handle 1K different address locations, right? And each location is of length 8 bit or 1 byte, right? So this is data, and this is for address, and this is for chip select, and this is for read and write, right? So you can see because we are having array of RAM chips, we have another circuitry, right? So that is a decoder. This is for memory enable, right? And this is decoder, and here we have dedicated 2 most significant bits to the decoder, address decoder, right? So this is the address, right? And here we have lines 1 to 10, right? So you can see that these 4 RAM chips, they are presenting the array of RAM chips, right? So this is the output, right? So here you can see that whenever we have decoder 00, so this 0 unit will be selected, right? And it can address 0 to 1023, right? And if we have 01 at decoder, right? So we will be having the next blocks selected, right? For decoder 10, this third block will be selected, right? And decoder 11, right? This block will be selected, right? So this is the size 4K into 8 RAM with 4 chips, RAM chips of size 1K into 8, right? So this is the and here we have read write, right? And you can see that the same read write is attached to each unit, right? And this is the chip select, right? And this is again the chip select, right? So whenever we have 00, it means this 0 is enabled and this chip is selected. When I have 01, 1 is enabled here, right? 1 is active here, and this chip is selected. And if we have 10, this is selected, right? Others are inactive, right? So this is 11, we have this chip selected, right? Other are inactive, right? So, and these are the address lines, right? And then we can also have the composite memory, right? So here we have what we have large number of words, right? So you can see that we have starting from 0 to 4095 words, right? Each word has length of 8 bit, right? So if I want to have a word that can have longer length, right? So here we have a 16-bit word, right? So what I did over here, I am using a composite memory, right? So this is one chip and this is another chip, right? So we have cascaded them, right? So this is the address, right? So again here address, right? So this is the chip select, right? And this is the read write, right? So this is the out, data out, right? And this is the data input. So we have constructed a composite memory, right? How we have cascaded those different memory blocks, right? So how the input lines are doubled, right? The output lines are also doubled, right? So 16 input and output data lines are split, between the two chips, right? Same IO bit address and the common chip select and read write control, right? So you can see that chip select is the same, read write is the same. So now we have the word of 16-bit each, right? So one of the problem with those different memory elements that they can have errors, right? Whenever we are storing data or we are retrieving data, right, from those different locations, right? So in order to make sure the reliability of that data, right, we need to make sure that we are actually receiving or retrieving or writing the correct data, right? So for that we need to detect errors, and after the detection we have to rectify the errors, right? So there are certain schemes which we can use, right? So the most common scheme that has been used is the parity bit, right? So what normally we do, parity bit is generated, right, and it has to be stored alongside the data, right, in the memory, right? So what normally we do, we generate parity, right, and we store that parity alongside the data, right? And whenever we retrieve data, right, obviously we come across the same parity, right? And if the parity check, and we check the parity, right, and if the parity check is correct, it means our data is correct, right? And it there is some error, right? So we can find out that there is some problem with the data, right? So this is error detection, right? So we need to do something else in order to rectify that error, right? So what we will be doing whenever we talk about error correction, right? So what we need, we acquire an error correcting code, right? So here we have the algorithm, right? So each check bit is a parity over a group of bits in the data world, right? So whenever we read the data from the memory, right, so obviously the parity bits that are associated with that word, they are also being read from the memory, right? And they are being compared with the new set of check bits generated from the read data, right? If the check bits compare, right, it indicates that no error is there. There is no error, right? And if the check bits do not compare with the stored parity, they generate a unique pattern called a syndrome, right, that can be used to identify the bit in error, right? A single error occurs when a bit changes in value, right, from 1 to 0 or from 0 to 1. Obviously we are dealing with binary number system, right? So that's why we will be having a change from 1 to 0 or from 0 to 1, right, during the read write operation, right? So what is the solution if we've identified an error at a certain bit position, right? So it has to be a 0 or 1, right? So if an error, particular or specific bit is having error, so what we will be doing, we will be taking the complement of that specific bit, right? So that is the code, error correcting code, which we will be using, Hamming code, right? So what we will be doing, right, k parity bits are added, right, to an n bit word. So now we have the new size n plus k bits per word, right? So the positions are numbered in sequence from 1 to n plus k, right? So those positions that are numbered as a power of 2 are reserved for the parity bit, right? The remaining bits are the data bits, right? So for an 8-bit data word 1 1 000 1 00, we include 4 parity bits with the 8-bit word, right, and arrange 12 bits as follows, right? So here we have identified the bit position, right, starting from 1 2 3 up till 12, and as we have mentioned that we will be having the parity bits at positions that are 2 raised to power, right, something, right? So 2 raised to power 0 1, 2 raised to power 1 2, and 2 raised to power 2 4, and 2 raised to power 3 8, right? If I will raise 2 raised to power 4, then we don't have those as much number of bits, that is equal to 16, but here we have 12 bits only. So here we have 4 parity bits, right, P1 P2 P3 and P4, and that are being placed in positions 1 2 4 and 8, right? So 2 raised to power 0, right? So this is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, and 2 raised to power 3, right? So I don't have 2 raised to power 4, right, because that might be 13, 14, 15, and 16, right? So we don't have 16 bits, we only have 12 bits, right? So, and then these are the bit positions, and here we are generating the parity, right? So this is the data, and you can see that 1 1, we have 1 1, and then 000, right, 000 and 000 here, and then 100, right? So 100. So this is the original data, but we have mixed the parity bits in a certain way, right? So how we will be generating the parity bits, right? So you can see that we have XOR operation between bits 3, 5, 7, 9, and 11, right? So this is 3, 5, right, 7, 9, and 11, right? And here we have the XOR operation for P2, right, 3, 6, 7, 10, and 11, for P4, 5, 6, 7, and 12, and for P8, 9, 10, 11, and 12, right? So what we will be doing, we will be placing the values of the corresponding bits, and we will be performing the XOR operation between them, right? So here even number of ones we will be having, because XOR operation, this is an odd function, right? So whenever we have even number of ones, we will be having 0. When we have the odd number of ones, we will be having 1, right? So even ones 0, odd one 1, right, odd one 1, right? So each parity is set that the total number of ones are even, right? So if I count total number of ones even, total number of ones even, even, and even, right? So here I will be checking the parity after the operation, read or write, whatever the operation is, right? So read from the memory, they are checked again for possible errors. The parity is checked over the same combination of bits, including the parity bit, right? So now we will be checking, right? So here you can see that C1, right? So you can see we are using the same, right? But we have added the corresponding bit 2, right? So this is the corresponding bit, and here again 3, 6, 7, 10, 11, right? 3, 6, 7, 10, 11, right? And the corresponding parity bit and 5 6 7 12, 5 6 7 12, right, and the corresponding. So this is the check. A 0 bit will mention an even parity over the check bits, right, and 1 will indicate an odd parity, right. So we have stored the bits while using the even parity, right, so that should result in 0 0 0, right. So if we got this, so it mentions, right, so that there is no error and the data is correct, right. So in case of error, right, so here you can see that we have the no error case, right. So error in bit 1, right, so bit 1 we have an error over here, right, and here we have an error over here, right, bit 5, right. So you can see that we are detecting the error, and we are also having the position of the error. So wherever we have the error, so what we will be doing for this bit 1, we will take the complement, right, so we will convert this one to 0. So here bit 5, this is 0, right, so we will converting this to 1, right. So again here those C's, they will mention no error, error in bit 1, error in bit 5, right. So you can see that 5 4 plus 1 5, right. So this is the algorithm for error correction, right, not only the detection but also the correction, right. So that's all for today's lecture. So in today's lecture we discussed about memories, right, and we talked about RAM particularly, right, and we also discussed different types of RAMs, right, and then we also discussed about different operations, right, that how we handle read and write operations within those RAMs, right, and then we talked about the combinational circuitry that is involved, right, in order to store and retrieve data from those RAMs, right, and finally we discussed about the error detection and error correction whenever we have to perform read and write operations, or in other words we want to store data or we want to retrieve data. So normally we come across different errors, so we discussed an algorithm that is being used for the error detection and error correction, that is the Hamming code. So that's all for today's lecture. So मेरी तरफ से अल्लाह हाफ़िज़, अस्सलाम वालेकुम.